So Pavel works at the Berkeley lab, and he has a background in mathematics, and he is the main developer of the refinement tools in the very popular Phenix package. So he's the main person behind Phenix Refine, and now he's going to provide an overview of the refinement tools that are available in Phenix. So please, Pavel.
Great. Thanks for introduction, and yeah, good afternoon, everybody. I'll now share the screen. Okay. All right, can you see my slides?
Yes.
Wonderful, and I'll go to slideshow mode. All right, well again, thanks for the introduction, and thanks for the opportunity to talk at this wonderful school. So really, I do have 15 minutes, and you can't really say much about refinement in 15 minutes. Really, it's a topic for a day lecture. So what I'm going to do is I'm going to provide some highlights and recent developments in Phenix, and some of them are particularly related to refinement. All right, like I said, I'm not going to go into any great details about refinement, but I'll point you out resources which you can follow and learn yourself about refinement and follow reference terrain. So there are two papers out there that describe real and reciprocal space refinement in Phenix in very great details. So again, if you want to learn about it, just follow these papers. And also, Phenix Online is a great resource for the educational information. Firstly, we have video tutorials and lectures which are on YouTube. There are a lot of lectures and tutorials. They are typically easy to follow, like 5 minutes long or slightly less or longer. A ton of presentations in PDF that basically the talks from past schools and workshops, and also cover most of topics. All right, so these are the resources that I would like to mention, and now I'll just go quickly and tell you what's new. And the first thing I'm going to mention is B-factor refinement in real space. In Phenix, real space refinement is the tool to refine atomic models against cryo-EM maps, or just generally maps. So, and up until recently, we've been missing an option to refine individual B factors. We only had an option to refine group B factors, and that was mostly because in cryo-EM we used to use low resolution data, low resolution maps, and there's no individual B factor that can refine against those maps. Now, with the high resolution maps, refining individual B factors is important. So now it's available in Phenix Real Space Refine. It's very fast. So now, again, like I said, you can do isotropic or group or individual B-factor refinement. It's totally symmetry aware, and by that I mean if map was symmetrized, then the B-factors will be identical across symmetry copies. You can use multiprocessing, so you can refine gigantic models relatively quick. Data to restraints weight is always an issue when it comes to refinement. So in this implementation, it's totally optimized. So the weight is optimized as part of refinement, so you don't need to think about it. It's all done as part of refinement. Now, just to give you a couple of hints, so when you do B-factor refinement, that's a typical question. And really, when it comes to cryo-EM, we refine B-factors as the very last step. This is because refined models do not feed back into maps in case of cryo-EM. So there's no point to refine them at each and every, your processes or cycle, right? Now, also question that comes, refined B-factor values depend on maps that you use. Think of original maps or sharpened maps. So which map do you use when you decide to refine B-factors? So I do not know the answer, and I just put that out there to stimulate a discussion on the topic. Okay. Next, also new is occupancy refinement in real space. Again, it's we added it several months ago. Like B-factor refinement is totally symmetry aware. You can use multiprocessing as well. And when it comes to occupancy refinement, it's quite complicated because there are many scenarios that can happen. You have partially occupied sites, you can sites that shared by different chemical entities, and so there are many scenarios. And basically what's available in real space refinement is similar to what's available in Phenix refinement, reciprocal space refinement. And again, I don't have time to go into details about it, but if you go to phenixonline.org, there will be a newsletter article describing 13 typical occupancy refinement scenarios and available options in Phenix Refine, and the same applies to real space refinement. And again, likewise, to B-factor refinement, you do refine occupancies at the very last step for very same reasons. Refined models in case of cryo-EM do not feed back into your data, into maps. All right. Now, we'll talk a little bit about validation because it really goes hand to hand with refinement, or refinement go hand to hand with validation. And validation is totally critical. And I hope everybody appreciates that. But here I will reiterate this again because I keep seeing situations where this kind of topic is overlooked. So here's why validation is totally critical. Here's an example of, well, a relatively recent structure published in Nature 2019. Just you can go to PDB and get that structure yourself. And it's the geometry of the structure is totally surprisingly poor. If you look at class score at 70, which is outrageous, Ramachandran favored 59, it's, you expect 98, right? 15% outliers, you expect 0 at this kind of resolution, Rotamers and so on. So everybody kind of sees that's pretty bad. And that basically means somehow validation stage was kept at this for this particular example. So why it's critical, you don't want to have something like this. Now, well, sometimes it's obvious, sometimes it's not. And here's another example, also quite recent, and also high-profile paper, where everything is pretty much perfect. So the geometry statistics is great. The model to data fit, I don't show it, but it's also great. Low class score, great from the channel plots, based on numbers. No outliers. So, well, you look at it and say, well, that's perfect structure. That's great, fantastic. But if you happen to plot, actually show the Ramachandran plot, it looks like this. And for a trained eye, or probably even for a newbie, it looks pretty unnatural. In fact, it looks awful. So that's not how a good Ramachandran plot supposed to look like. So and you'll ask yourself the question, well, what happens if I don't look at this plot? What happens if I just look at that table of numbers of statistics? Then you will miss this bad situation. And so how you detect this problem, and that's how you do it. And again, I don't have time to go into great details, but I refer you to this relatively recent paper where we reintroduce and discuss a new, relatively new metric that we call Ramachandran plot Z-score, or Rama Z. And that's really a single number that you can calculate for a structure, and that can tell if the structure is bad, good, or suspicious in terms of Ramachandran plot. So very useful metric that's trivial to calculate. Just one number, you look at that number and you immediately know that problem without even looking at Ramachandran plot. I'm not saying it's not a good idea to look at plots. It's a good idea to look at plots and all the statistics you can have, but that's an easy way to highlight problems, and also that's a good way if you have pipelines and you need to train software to make numerical decisions. Then of course that's helpful if you can go by numbers rather than a human being looking at plots. So now that number is consistently reported in Phenix, and we encourage everyone to use it. Also available in PDB redo as well, because that's kind of the idea comes from that end. All right. Now I'll just briefly mention validation of predicted models. As you all know, this AlphaFold thing is the topic, is the theme these days. And those are recent question on CCP for mailing list. How do I validate predicted models? Well, let's just define what is validation in case of structural biology topic. So basically, validation is all about making sure that model data, be that cryo-EM or diffraction data, and model to data fit all make sense in all different kinds of senses, physical, chemical, common, and so on. So that's what validation is. Now, again, in case of our usual scenarios, we have cryo-EM or diffraction data. But now, if you have predicted model, you don't really have diffraction data. You don't really have cryo-EM data. I mean, I'm talking about the case where you just have a predicted model with no any experimental data. In that case, really the answer to that question is, well, you still have a model, and model doesn't care what method you use to determine it. So, I mean, alpha helix has alpha helix geometry, no matter what method you use to determine that alpha helix, right? So, and then the answer to that question is most model validation methods still apply, and of course, plus some validation specific to prediction methods as well. Now, AlphaFold, like I said, is the theme these days, and AlphaFold in Phenix. So we do have recent additions to Phenix, which I highlight in red here. So now in Phenix View, you can find a whole slew of AlphaFold related tools, and they're pretty much straightforward to follow. Well, the whole thing starts with how to use AlphaFold in Phenix, and if you click on that, you'll get a comprehensive tutorial and step-by-step instructions on how to use AlphaFold in Phenix. And there are different tools that are useful and handy when you use AlphaFold in Phenix. They're all described in this tutorial. So this is available in very recent versions of Phenix, mostly done by Tom Terwilliger, Dorothy, Christopher, and others in our Phenix team. Now, this is a busy slide, but I'll just so you understand what kind of the workflow when you use AlphaFold within the Phenix context. So basically, it's typically 6 steps. Well, first you get an AlphaFold model, and in the GUI there's a button that you just click, enter sequence, and off you go. Then once you get the model, you trim that model and break into rigid domains, and depending whether it's cryo-EM or crystallography, you do docking or molecular replacement. You do docking with this Phenix tool, dock predicted model, or you use standard phaser to do MR with this domains. And then once you've placed model into where it belongs to with respect to data, you fill all the missing parts by doing automatic rebuilding. You just realize that models are not going to be 100% complete, 100% accurate. So, I mean, predicted models. So you still need to do some work to fill missing bits and parts of that model. And again, we have 2 tools to do that. One is for crystallography, for cryo-EM, and the other one for crystallography. So it's all available in latest Phenix versions. And once you completed your model, you go to refinement. And as I mentioned earlier, 2 tools are available in Phenix: refinement, real space refine, that's for cryo-EM, but you can use any map, and Phenix refine for crystallography. So, and the 5th step, we get your refined model. Of course, it's not going to be perfect just for the first round. So, usual practices apply here. you inspect and validate, and you go back to step 5 if needed to, hand tune your structure. But this is kind of overview of basic steps, general steps when it comes to use AlphaFold within Phenix context. Now, just a quick example. This is done by Tom Terwilliger. So this shows how well AlphaFold can perform, and also it doesn't perform all that well, and the importance of this rebuilding stage. So this is an example of 7M.js structure. The yellow is deposited structure from the PDB, and the blue one is what you get straight out of AlphaFold. As you can see, it's done good structure, so it predicts most of it, and it does very excellent job doing so. Although, as I mentioned, there will be always bits and structures where it didn't do all that well, and typically these are, some loops and some flexible parts. And this is where automated rebuilding comes handy. So on the right is basically we take the AlphaFold predicted model and submit it to our automated building procedure in Phenix, and it basically leaves the good parts in place and does a good job on rebuilding parts that AlphaFold missed. So of course it doesn't work. All right, it doesn't work all the time this way, but this is kind of typical example that we are observing so far. All right, the other thing, and I'm almost done. The other thing I wanted to mention, and this is not very new, this guy, I think Dorothy talked about it last year, but it's kind of a year and a half old feature in Phenix. So we have a Ceres server in Phenix, which is kind of PDB redo, but for cryo-EM. It's basically monthly re-refinements, sort of totally automated monthly re-refinements of all cryo structures available in the PDB database. And that's presented as a nice web feature where you have tables of all the structures with reported statistics and redefined statistics. And, this is useful. I mean, I'm not going to say anything like, we're not going to blame anyone, and we're not trying to outdo PDB. It's just useful for developers to help track the impact of new methods and tools, because we can go back in time and see how Phenix refinement performed a year ago and how it performs now. So it's helpful, right? And for users, it lets to see how the models can potentially be improved using the latest methodology and tools. So again, you may find your structure 10 years ago, and you can see how better it can become with using tools these days. All right, just almost the last slide. Like I said, very hard to cover everything in this short period of time, but there are channels that you can use to ask questions and get back to us with feedbacks. So there's a mailing list in Phenix. I always show this part because that's very important, and we have a lot of users that come to us with questions and problems. So if you have any problems or bug reports and you wanted to share it with us, then really we can't help you if you don't help us to understand your problems. And what that involves is, if you decided to report it back, we need to really send us enough information so that we can be helpful for you. Like, you need to say version of the software you used, what commands or what click in the GUI, all the input and output files, and clearly explain the problem. And when you send files to us, only developers sees these files, and they're not going to share these files with anyone. So that happens totally confidentially, and it's totally safe to do. And of course, subscribing to the mailing list is a good idea. Final slide, that's the thank you slide to everybody working in Phenix, all the collaborators. And with that, I am done with my talk, and I'm happy to take questions. Thank you.
Thank you. I think we are running out of time, but I will allow 2 questions. two questions from question and answer. How does the Ramachandran score looks like for the 6KS6 example shown?
Yeah, I don't have number right in front of me, but basically the idea is that anything that is less than -3 or greater than 3 is bad, between 1 and 2 is suspicious, and less than 1 is good as expected. So you can follow that paper to find the guidelines for the number, that the clear guidelines explaining how to use this number. So basically, the paper will explain how to interpret these numbers. But I don't have particular number for that example at hand right now.
Thank you. I'll read Andrea's question also, and at the same time, I will move this question to Slack so that you can answer those questions. So Andrea asks that as the field moves to use AlphaFold models as starting points for structure solution, geometric validation may no longer be as useful. And density maps are not always corresponding well enough models to be useful validation alone. What's your take on that?
Yeah, I mean it's a complex topic, of course. Well, I would say I would still think that standard traditional model validation tools are important. And once again, I mean, look at AlphaHelix. It has a geometry, and it does not, and that geometry should not vary depending on what method you used to obtain that geometry, whether that crystallography, prediction, or cryo-EM. So there's no reason why AlphaHelix suddenly shouldn't look like an AlphaHelix because you used prediction. So, and that is my logic to say that standard validation methods still apply for predicted models. Right.
I think that the rest of the answer and discussion should be on Slack because we should respect for next speakers also. Thank you.